Alright folks, welcome back to the part 3 of lesson 1. In this lesson, we'll learn the move syntax basics. So this is the agenda for this lesson. We'll focus on the move syntax basics, and throughout this lesson, we'll learn the syntax and some key features of the move language compared to other programming languages. Firstly, we'll introduce move module and package, and they will describe how move projects are organized. Then, we'll learn the move syntax basics including data types, control flow, and functions. Lastly, we'll give you some exercise to consolidate those knowledge. Alright, let's start with move module and package. And they describe how move code is organized and what the project structure looks like. The main unit of move code organization is a package. A package consists of a set of modules defined in separate files with a .move extension. These files include move functions and type definitions. If you're familiar with Java language, then you'll be noticed that the modules and packages in Move are pretty similar to the ones that in Java. And as you can see here, the left is a Move package named myMovePackage, a set of files on the disk. And the sources subdirectory is source code files where one or more modules defined are located. We'll introduce move.toml and move.log later. And the right is a move module named myFirstModule, written in myModule.move file. And as you can see here, module is just a set of move functions and type definitions defined in separate files with the .move extension. Okay, now let's introduce the move module syntax. A move module has the following syntax. So all the elements inside a module block can appear in any order. Fundamentally, a module is a collection of types and functions. The use keyword here is used to import types from other modules, and the frame keyword here specifies a list of trusted modules. And in the end, the constant keyword defines private constants that can be used in the function of the module. Also notice that module is a built-in keyword. Address is a value name or literal address. Identifier is a module name. So in this code example, the module Alice, myFirstModule, specifies that the module myFirstModule will be published under the name address Alice, which is specified in the move.toml file. And the name address Alice only exists at the source language level, and during compilation, name address will be fully substituted for their value at the bytecode level. Alright, for the naming of the module names start with letter A to Z or capital letters A to Z. And for the first character, module names can contain underscore letters A to Z, capital letters A to Z, or digits 0 to 9. So typically, module names use snake casing. For example, my_module. A module named my_module should be stored in a source file named my_module.move. A move package is just a collection of modules with a manifest file called move.toml. It's a unit which is published on-chain. Packages allow move codes to be reused more easily and to be shared across projects. A package must include the move.toml manifest file, describing package configuration, such as package metadata and package dependencies. And the package naming conversions also use snake casing-like modules. A module name uses a path separator semicolon to divide the package name and the module name. So for example here, unit1 semicolon hello world. So the hello world is a module in unit1 package. And same thing here, cappy. So it's a cappy module in cappy package. For the package, and for the move.toml file in the package. So move.toml is a manifest file of a package and is automatically generated in the project root folder. And it consists of three sections: package, dependencies, and address. Package defines the name and version number of the package. Dependencies defines other package that this package depends on. Address defines alias of address in the package source code. Alright, this is a code example of the package of the move.toml file. So we see that we have the package with name hello world and also the version 0.0.1 with the dependencies of only the suite as the only dependency. So we see that the suite standard library dependency is defined using a GitHub repo here, but it can also point to a local library using its relative or absolute file path. And the address here is pretty simple. So this is a move project source directory contains a move.toml package manifest file along with a set of subdirectories. The directories marked required, so move.toml and sources, must be present in order for the directory to be considered a move package and to be compiled. Optional directories can be present, and if so, you'll be included in the compilation process. So depending on the mod that the package is built with, test or dev, the test and example directories will be included as well. The sources directory contains move modules. The example directory can hold additional code to be used only for development or tutorial purpose that will not be included when compiled outside test or dev mode. A scripts directory is supposed to do transactions, and it can be separated from modules if that is desired for the package author. The scripts directory will always be included for compilation if it's present. Documentation will be built using any documentation templates present in the doc templates directory. And the last one is the test. And if you have any unit tests or more tests, you can also include them. Okay, a package can be compiled through the move command line interface commands, which we mentioned in the last class. This will create a compiled package that holds a compiled bytecode along with other compilation artifacts. For example, the source maps, documentations, ABIs in memory. So this compiled package can be converted to an on this package and vice versa. The compiled package lay out in the file system in the following formats. Alright, so in this section, we'll then introduce the basic data types and their operations in Move. So there is a built-in types which is integers. Move supports 6 unsigned integer types: U8, U16, U38 until U256. And notice that there is no signed integers, because in asset-oriented smart contract programming, this is a rarely case and we don't need negative numbers that much. And here is some examples of how to declare unsigned integers. So you can start with literals with explicit annotations. For example, you can have the U8 after the 1, and also U64 after this number. But you can also have the literals with simple reference inference. So for example, like you declare the types here and the numbers here. Okay, and the operations between integers are most likely in other programming language. Each of these types supports the same set of checked arithmetic operations. For all of these operations, both arguments, the left and right side operands, must be of the same type. So all arithmetic operations abort instead of behaving in a way that mathematical integers will not, like overflow, underflow, divide by zero. So if you need to operate over values of different types, you need to first perform a cast. Similarly, if you expect the result of the operation to be too large for the integer type, you need to perform a cast to a large size before performing the operation. Integer types of one size can be cast to integer types of another size. Integers are the only types in Move that supports casting. And notice that casting do not truncate. So it will only abort if the result is too large for the specified type. This is because Move is a very strictly static type programming language designed for security. And here are some examples. To cast X as U8, cast Y as U16, and cast this number as U32. For the Boolean, so Boolean is Move's primitive type for Boolean values, true and false. And we have the logical operations, the and, or, and negation. Address is a built-in type in Move that is used to represent locations in global storage. Address value is 256 bits, which is also 32-byte identifier in SwiMove, which is pretty different with that in Move. At a given address, SwiMove objects can be stored, but note that Swi global storage is different from Move. It uses SwiMove objects as global storage, which we will cover in a later session. Okay, here is address syntax. So the address can be used as an expression. The address must be prefixed by the @ character here, and it can be numerical values like 1, 42, 66, something like that, or the name address identifier, for example, STD. And outside of the expression context, the address must be written without the leading @ character. So as you can see here, they don't have the @. For the vector T is the only primitive collection type provided by Move. A vector T is a homogeneous collection of T's that can grow or shrink by pushing or popping values off the end. A vector T can be instantiated with any type T. In SwiMove, vector and vector-backed collections, vector, vexec, vecmype, priority queues should have a maximum size less than or equal to 1,000 items. And we'll review the homogeneous collection in later chapters. Okay, so here are some data types of the vectors in code example. So basically, this will create an empty vector of type T. And this one will create a vector of size 1. This one, pushback, will add T to the end of V. And append will add the elements in V1 to the end of V. So you can check those functions and code example later on, and we won't go detail of them. For the structs in the data types, so a struct is a user-defined data structure containing typed fields. Structs can store any non-reference type, including other structs. Structs must be defined inside a module, and structs cannot be recursive. So here is a code example of some structs. For example, the structure full. So as you can see here, the x and y are the fields of full, and field can be any non-reference type. And we have another structure bar. So bar can have the structure full as its field. However, we cannot allow the full to be recursive here. All right, so for the type abilities, abilities are pretty crucial to define how objects behave in Move at the language level. Each unique combination of abilities in Move is its own design pattern. So custom types that have the key ability are considered to be objects in SweetMove. Objects are stored in global storage and can be transferred between accounts. We will study abilities and how to use them in Move throughout the course. So we have 4 type abilities here, and basically they are copy, which means value can be copied, and drop, which implies value can be dropped. Then key allow the values to be used as key for global storage operations. And finally, we have store, which enables value to be stored inside the global storage. Okay, but what if there is a structure that don't have any ability? And here is the example of it. This is a pretty magic program pattern in Move, which we call a hot potato pattern. So the structure recipient does not have the key or store ability, so it cannot be transferred or otherwise placed in persistent storage. It also does not have the drop ability, so it cannot be discarded. Thus, the only way to get rid of this structure is to call repay sometime, so call this function after you have the recipient in the loan. So sometime during the transaction that creates it, which is the loan function. And this is exactly what we want from a flash loan, because in this case, you want to get the loan and repay it back at the same transaction. Right, so the local variables and their scopes. Local variables in Move are statically scoped. New variables are introduced with the keyword let, which will shadow any previous local with the same name. Locals are mutable and can be updated both directly or via a mutable reference. So Move programs use let to bind variable names to values. And let can also be used without binding a value to the local, like this. And variables must be assigned before use. However, notice that we cannot start with uppercase letters. In this section, we'll introduce the control flow of Move, including conditional control and loops. So an if expression specifies that some code should only be evaluated if a certain condition is true, and can optionally include an else to specify another expression to evaluate when the condition is false. And the conditional expression might produce values so that the if expression has a result. Let's say the code example here. So in this statement, it says that if y is less than or equal to 10, then y will be assigned to y plus 1. If else, so for example, y is 11, then we'll reassign y to 10. Okay, another one is like we can also produce the values. So we'll let z equals x if x is less than 100. And if x is equal or more than 100, then we'll let z equals 100. Yes. The while construct repeats the code body until the condition evaluates to false. So in this example, the function sum defines the sum to be 0 and I to be 1. And while I is less than or equal to n, then we just append or add I to the sum. And n is passed by the parameter here. So basically, this function just adds up all the numbers from 1 to n and print out the sum. Yeah. The loop expression repeats the loop body until it hits a break. So without the break, the loop will continue forever, and you should notice that. In this subsection, we'll introduce move functions, including function signature, visibility, and invocations. So functions are declared with the fun keyword followed by the function name, type parameters, return types, and finally the function body. So move functions have three types of visibility. Private, which is the default setting, public, and public friend. So private functions can only be accessed by functions inside the same module. Public functions are accessible by any module, while public friend functions is accessible by functions inside the same module or by functions defined in modules that are included on the module's friends list. So let's say the example here. As you can see, here is module M under the package 42. All right, and it defines n to be its friends. And here is a public friend function called foo, in which case only n can cause it, or other function inside of this function can cause it. Then there's a public function bar, so any module can cause it. And finally, here is a private function foo, and this can only be callable by the inner functions. Okay, here is another module n. So it defines a function cosm. Firstly, it'll let underscore equals m's module semicolon foo. So because foo is a private function, sorry. Because foo is a private function, so it cannot be accessible in other modules. And then it calls a bar function. Because bar is a public function, so it can be accessible by all modules. So that's a valid. And lastly, it calls a call foo. Because n is a friend of the module m, so it can also be accessible by n. And here is the other module of so you also have a cos m. The first one is it calls m modules foo function. And same thing here, right? Because foo is private, there's no way that other can call some m's foo function. The second one, m's bar function, because bar is public, so anyone can just call it. The third one is cos foo. So cos foo is a public friend function. However, other is not a friend module defined inside of m. So other cannot call m's call for a function. And that's pretty much the function visibility here. We have one extra entry modifier. So a move functions with entry modifier means it's the beginning of an execution, and functions that can be directly called by a transaction. Essentially, entry functions are the main functions of a module, and then specify where move programs start executing. There can be directly called by a transaction. Note though, an entry function can still be called by other move functions. So while they can serve as the start of a move program, they aren't restricted to that case. In general, an entry function must satisfy the following properties. It has to have the entry modifier, but the visibility does not matter. It also has no return values. Alright, there is a code example that's showing this. So both of these are the entry functions, but the first one is a public function, and the second one is a private function. But as we said, the visibility does not really matter. For the parameters of the function parameters are declared with the local variable name followed by a type annotation. So for example, x followed by u64, and we read this as x has type u64. A function does not have to have any parameters at all, so this is a valid function. And the return type of a function, so the return type is specified in the function signature after the function parameters, separated by a colon. A function's last line without the semicolon is the return value. A function can return multiple values by using tuples. A function can have no return type specified. Right. So here are some examples of return types. We have a single return type, several return type in a tuple, and no return types. A function body is an expression block. The return value of the function is the last value in the sequence without a semicolon. You can also use the keyword return to return value directly. So you can add a return here. When calling a function, the name can be specified either through an alias or fully qualified. Every parameter must be given, no default values. Alright, so with the use above, all of these calls are equivalent. We have a use here, so we can define the zero function with fully qualified, or the module name, or just zero. Type arguments can also be either specified or inferred, so both of these cases are valid. Alright, finally, we'll give you some exercise to consolidate our knowledge. The exercise will involve structure definition, ability usage, function implementation, and return values, etc. Okay, you will try to complete the given store modules. There is a store package. It has the bread store and pet store modules. Please finish the below tasks. Define the sandwich structure in bread store. Finish the buy sandwich function in bread store and implement the pie store module. Publish the package to SuiteDevNet and call the entry functions. You can check the below documents for further details. Okay, so you can post now and come back later. Alright, Here is another exercise. You need to try to complete the sandwich module. And the core of it has a grocery where user can buy ham and bread. User uses ham and bread to make a sandwich. Users can eat the given sandwich or store the given sandwich in his account. The grocery account owner can collect profit of selling ham and bread. You can also check the exercise doc here. So this is a grocery definition. You should define your ham, your bread, and sandwich structure here. And for implementing these functions, you have the initiate, buy ham, buy bread, and make sandwich. So initiate is on module initiate. It will create a grocery and send the grocery owner capability to the module published. Buy ham will just buy ham with some sweet token, and buy bread will just buy bread with some sweet token as well. Make sandwich will combine the ham and bread into a delicious sandwich and return. You'll also need to implement those functions: the eat sandwich, store sandwich, and collect profits. So eat sandwich will consume the sandwich, store sandwich will send the given sandwich to the sender's account, and collect profits will enable the grocery owner collect profits by passing his capability and transfer all the profits to the owner address. All right, so here is a reference you can check on to consolidate your knowledge and also do the exercise. And I wish you like this lesson. I'll see you next time.